We now have our points out here in these pressure areas, and the question is how to get the velocity vectors pointing towards the surface. We do not want to turn this into polygons because doing that will be a very expensive calculation, and that'll take up your sim time quite a bit. So instead, what we'll do is we'll take our density and we'll scatter points in areas where the density is less. That would be probably towards these fringe areas anyway. So if we, let's say, sectioned off density so that only the values that were 0.1 were left, that would give us some points along the edges here, and that would give us the ability to find the nearest points and set the velocity vector in that direction towards the plume. Let's go ahead and create a copy of this pressure import and turn that into a density import. So we'll say this is our density import. And like I said, all we need to do is isolate the areas where the value is pretty low on the density. So if I create a volume wrangle, this node is going to perform very quickly. And that's why I'm using that in particular. So what we could say is that if the density is, let's say, less than, or let's say greater than 0.1, then go ahead and set density equal to 0. Close curly bracket right there. So that will isolate any areas that are greater than 0.1 in the density. To check this, let's go ahead and move forward 30 frames on our DOPNet and make sure that that volume is actually showing up properly. And yes, in fact, we are isolating these areas like so. However, 0.1 is too small. So let's bring this maybe to 0.5. And now we're really just getting those edges a lot better. So once we have these edges, all we need to do is scatter some points and turn off the relax iterations right there, and then add a bunch of points from here. So I'll say maybe we can add about 5,000 or so points. That's pretty good for what we need. Also over here on the scatter, let's also turn off the relax iterations because again, that takes a lot of processing time. So turn that off over there. Now we need to figure out how to take these points in the pressure areas and get them to look at these points when deciding on velocity. So we've already done this trick before in SOPs. Let's go back to our velocity section real quick and simply just copy what we had here in this wrangle, where we set the velocity for our, stenciled area. So we'll copy all that code, go back to the DOPNet, and create a point wrangle. Plug that in, first inputs. The second inputs is going to be after the scatter. And what we'll say is that we don't need this whole section where we masked off that whole effect. We just need the nearby points and the position. Also, we don't need the sampled vel mask. However, I do want to multiply our velocity by something, so let's create a new variable right here. We'll call this our velocity scale, so vel scale is equal to a channel vector that, again, is called vel scale. And then we'll take this entire thing and multiply it by our vel scale, like so. We could turn this up to, let's say, a value of 5 to start. And this is going to error out because I was, interrupting the cooking. So let's try to re-kick this by going up to the DOPNet again and trying frame 30. And now we are back. Let's go ahead and switch these inputs. I actually have them mixed up right now. So we'll just go like that and turn on our trails. So we can see that these guys are now generally pointing towards the plume. And if I template this and I bring back our fog volume, you can really see that in action. These guys are pointing towards the plume. They are specifically in areas where the pressure is present, where the plume is expanding. So that's the areas that would experience the cold air. And now the last thing that we need to figure out is how intense we want to make this velocity. And there's multiple ways of doing this. One way that I like doing this is to start by taking our velocity field and doing a volume sample of that, or a volume slice, that is. So let's bring in vel right here, volume slice. We are now sampling velocity. And this attribute right here can be seen in our geo spreadsheets. So if I sort by the most intense velocity in the y direction, we have a value of 76. The most intense value in x is 51, and in z it's 56 as well. So what we can do is try to go for one of these components. However, it's better to actually just take the magnitude of this velocity, or the length of that velocity vector. And so all we need to do is create a point wrangle. And from here, I'm going to create a new attribute called magnitude. And that's equal to the length function. The length takes the length of this vector. So if we imagine that arrow drawn out, it's the length of that arrow. Let's take velocity right there. And there we go. Now we have the magnitude. So once we have that magnitude, how do we want to use this information to inform the velocity that's generated by that wrangle over there? Well, we could just take the maximum magnitude. In practice, I find that that's a bit too strong, usually. So when we do an attribute promote, I like instead taking the average of the magnitude. And so let's take our magnitude right here and promote that to the detail attributes as, again, an average promotion method. So that leaves us with the magnitude of 9.6. Now at our point wrangle, we can go over here, right click. Let's go ahead and reference scene data. Go over here, and under attributes, global magnitude, we can take that value and have it reference over here like so. Let's also take this and paste as a relative reference for y and z, like so. And I found that the average is about the right value. I like going up a tad bit from that, so this will be times 1.5. So just up a little bit from where that was. So now, let's go ahead and re-kick our scene here. So reset sim, and then we'll go forward 30 frames, and we'll recheck everything. Okay, and now we have this. So there's our velocity vectors. They're pointing towards the plume. That's pretty much good to go. Let's give ourselves some more room over here. So we'll take this down, and we want to take this point wrangle and plug that into the point velocity down here. For the basic tab, let's say keep incoming, and then we'll take our conical noise and maybe turn this to a value of 1 or 2. Not anything too high, but just a little bit to give us a bit of randomization in the direction. So once again, back to the .NET, frame 30. Let's see what those vectors look like. Okay, and as we can see, there is the difference. So that will add just a tad bit of variety. We can also do a curl noise if you want, but I just like a little bit of conical noise. That will do just fine for the situation. Okay, we also have this currently as V, so that then becomes vel. We have our P scale. I would like to turn up this P scale a bit. So let's say 0.3 on that, and then the min value is going to be 0.5. And I think that's all we need to get this going. Let's see what the effect is when we have maybe a few more particles here as well. So instead of 250, let's go ahead and make this about 400 or so. Let's see what this does to our simulation. Now, as you can see, we have all that breakup happening, which is really cool. What is also happening, though, is that we don't really have temperature pulling things upward enough. And so one thing I want to do to fix that, and we should have done this earlier, but oh well, we can go to our pyro solver here, go to flames, and I do not want to pull right there. I want to add with fuel. So once we add, set that to about 0.5, and that'll add a lot more swirly motion through that whole buoyancy trick. Anyway, that pretty much does it for setting up these guys. Let's see what happens when we have both the interior particles affecting fuel, as well as our exterior particles rendering out. And now we have this, which right now is looking pretty fluffy. It's looking maybe a little too fluffy for my taste, but the point is that that velocity on the outside, that cold air, is really adding a lot of detail to these shapes, especially earlier on in the simulation around here. And so we have a lot of really cool detail happening as a result of all the various things that we're doing. And well, we can do a few things to dial in the shape of this so it's not so much of a floofy blob, but we know that in general the behavior is working, and that's awesome. In the next video, let's move on to microsolvers.